Hi Science 30s, Mr. Riley here. I'm going to do a quick little video looking at what's called electromagnetic induction, and it's one of the coolest physics principles that you are ever going to learn. And what it's all about is that there is a connection between electrical current. Let me just, I guess, get a pen here. Current and also a magnetic field. And so I can put a current through a wire, and I can induce or produce a magnetic field, and I can also take a magnetic field and I can induce a current in a wire. So there's three applications of this that we're going to just look at briefly here. So the first would be an electromagnet. So if I take a wire and specifically multiple coils of wire, and I put a current through it, I essentially turn it into a magnet with a north and a south pole. So the picture on the left here is an electromagnet, and I can turn it on and off by turning on and off my power source. And on the right we have a permanent magnet. And we can see that the field lines are identical for each of these. Now, electromagnets have a bunch of applications of their own, but I think that the two greatest, or I guess the best applications of these are what we're going to look at next here. So this image right here is a DC motor, and how this motor works is we have a power source down here. Okay, it is going to send current into this. Now this is a what we call a brush, and this is a ingenious piece of engineering that allows electrical current to be conducted without having a permanent connection. So it's two pieces that can slide past each other and conduct electricity that way. Now that goes into this part right here, which is called the commutator, and it's not a complete ring, it's a split ring, and that is really, really important because this is attached to what is essentially an electromagnet. So this part right here, this is an electromagnet with north and south poles. These right here and here are permanent magnets. So essentially how a motor works is the electromagnet and the permanent magnets are constantly attracting and repelling each other, and the electromagnet is on some kind of pivot that allows it to turn. So what happens is we get this constant attraction and repulsion between these two magnets, and that's what makes a motor spin. That's a motor. And the reason we have this sort of split ring deal right here is paramount to this thing working properly. And that is that every half turn, the poles of the electromagnet are going to flip. Because if that didn't happen, then, if let's say this is the south and this is the north pole of my electromagnet, then what's going to happen is it's going to, when it hits that point, these north and south are going to be attracted to each other, and it's going to stop. It's only going to turn half a turn. But if every half turn we flip the poles, then it's going to continuously getting attracted and repelled. Okay. So one thing important to know for a motor for us is the energy conversions. So in a motor, we are going from electrical energy to mechanical energy. Okay. So we have some kind of electrical source, maybe it's a battery, and we're turning that into mechanical energy. And in this case it is a battery because I'm dealing with what's called a DC motor. Okay. Now below here we have the opposite of a motor. This is a generator. So a generator, you're going to see here, looks very similar. Okay. I have to have some kind of mechanical input. So this could be falling water, this could be steam turning a turbine, this could be somebody cranking it with their hand. And we are what we're doing here is we're going to induce a current. We're going to use a moving magnetic field to induce a current and produce this electrical output. Okay, so this one right here is actually what we would call a DC generator, so direct current. But most generators we use are AC generators, because our homes run on AC power. Power stations generate AC power because transformers use AC power. So what you would want for an AC generator is you would not have a split in this ring. You wouldn't want the the current to move all in one direction. So you wouldn't want to continuously switch the poles on your magnet. You want to keep them essentially the same way, so your current keeps flipping back and forth. Okay, so what we want to know about generators is, well, it's the opposite of a motor. So we're going from some kind of mechanical input to an electrical output. Okay, and we need to have a moving magnetic field to induce the current that's going to enter into the conducting wires. Okay, so that's a little bit about electromagnetic induction. Good luck. I'll see you next time.